Okay, in this video we're going to start to prove part 2 of the fundamental theorem of calculus. So I'm starting with the definite integral of big F prime of x dx. I'm hoping to get to big F of x just evaluated at b minus what we get when we evaluate at a. Okay. Now, this is going to be a fairly long argument. Okay. So I want to let you know from the get-go, I am not going to ask you on an exam to prove the fundamental theorem of calculus. Okay, that would be too much. That said, I'm not encouraging you to pause the video and just keep it paused and never come back and watch the derivation or the proof of the fundamental theorem, because I do think it's fairly instructive. So, what I can do with this is what I've said in the past as well. I wouldn't ask you to reiterate this proof and come up with it all on your own. But I could ask you some questions about it. So I could say, when we were proving this, there was this point where we did this. What was the next step? So I could ask you to do just a part of things. So I do want you to study this proof, but don't feel like you need to memorize it. Just don't feel like it's something that you need to shy away from either. Okay, so that's a definite integral. I know that's going to be a limit of a Riemann sum. So I can write this as the limit as n goes to infinity of the sum as I goes from 1 to n of f prime of xi star times delta x. Now this would be the area of a rectangle where I'm using this as my height function. So this would be my height, and this would be my base. Okay, so the key to this proof is going to be in how I choose my sample points. I'm not going to just choose right endpoints or left endpoints or anything like that. Okay, here's what I'm going to do. I'm going to suppose that this is the ith subinterval right here. So that would be going from x sub I minus 1 to x sub I. Okay. And I'm going to draw here a graph of f of x. Not my integrand, which is f prime, but my antiderivative. Because I know where I'm trying to go with this. I'm trying to get to just f of x evaluated at b minus f of x evaluated at a, and that's what I want. But right now, there's no f. I'm talking about f prime. I'm talking about the wrong function. I need to somehow find a way of switching to talking about my function f, which I know is supposed to show up, in my final answer. Okay. So, I'm going to observe that f of x is continuous on the interval from x sub I minus 1 to x sub I. Now I know that because it's differentiable, because I'm integrating its derivative. And we had a theorem way back when that said that if a function is differentiable, it has to be continuous. Doesn't work the other way. It can be continuous but not differentiable, and the absolute value function is the classic example of that. Okay. But if the derivative exists, it's continuous. Okay. I'm also going to point out that that means f of x is differentiable on the open interval from xi minus 1 to xi. Now I actually know more than that. It's differentiable on this closed interval because it's differentiable on the entire interval from a to b. But this is what I need right here. This should remind you of a theorem we had. These are the two hypotheses of the mean value theorem. And what the mean value theorem said was if you have a function that's continuous on a closed interval, differentiable on an open interval, then by the mean value theorem, there exists an x value. Now usually we've called it c. I'm going to call it xi star instead, in this interval between xi minus 1 and xi. So somewhere in this subinterval there's an x value such that f prime at xi star, which would be the slope of the tangent line there, is equal to f of xi minus f of xi minus 1 all over delta x, which would be the length of this subinterval here. That's just the slope of the secant line. So if I take a look here, there's the secant line connecting those 2 points. Now, according to the mean value theorem, there's got to be some point, and it looks to me like it's right around there, where the tangent line is parallel to that secant line. I'm going to choose that to be my xi star, because that way I'm now able to describe f prime at xi star in terms of the function f. So this is the key that's going to allow me to switch from talking about f prime to talking about f. Okay, so let's see what that gives us. So with that choice of xi star, so I'm going to just say choosing xi star as guaranteed to exist by the mean value theorem. I'm going to get the limit as n goes to infinity of the sum as I goes from 1 to n of, I'm going to replace this expression for the slope of the secant line with this expression for the slope of the, this expression for the slope of the tangent with this expression for the slope of the secant. So it's f of xi, that's my right endpoint, minus f of xi minus 1, that's my left endpoint, over delta x times delta x. Okay, so just to remind you, when we partitioned the interval from a to b, anytime we do a partition, we just name the endpoints. So we start with x sub 0 being a, and then x1, x2, etc., b would be x sub n. Okay. So that's why when I was on the ith piece, I said the right endpoint would be xi, the left endpoint would be xi minus 1. Okay, I feel like canceling a delta x. Okay, so I cancel the delta x. Feeling good about that. Okay, now what I'm going to do is I'm going to write this out. Instead of using the sigma notation, I'm just going to use the dot, 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 the ellipses to indicate that my pattern continues. So I've got the limit as n goes to infinity of. Now, when my index is 1, what I'm going to get is f of x1 minus f of x0. Because for the first subinterval, x1 is the right endpoint and x0 is the left endpoint. Plus, when my index is 2, I'm going to be getting f of x2 minus f of x1. Because for the second subinterval, x2 is the right endpoint and x1 is the left endpoint. Plus, when my index is 3, I'm going to be getting f of x3 minus f of x2. x3 would be my right endpoint, x2 is my left. Plus, dot, 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 dot. Okay. Plus, finally, for the last piece, I'll get f of xn minus f of xn minus 1. But you'll notice x1 shows up twice. It shows up once positive because it's the right endpoint of that first subinterval, but it shows up once negative because it's the left endpoint of the second interval. Now the same thing happens for x2. It shows up positive here because it's the right endpoint of the second interval, But it shows up negative here because it's the left endpoint of the third interval. And in fact, almost all of these x values, all of the ones in the middle, are both left and right endpoints. They're the left endpoint of the interval that are to the right. They're the right endpoint of the subinterval that's to the left. So we're going to get the function evaluated at them twice, once positive and once negative. The only ones for which that won't happen are the very first and the very last endpoint. Because x naught here, that's a left endpoint for that subinterval, but it's not a right endpoint for anything. Similarly, xn, that's a right endpoint for the whole thing, but it's not a left endpoint for anything. So, this is what we call a telescoping sum. It's something that starts out looking huge, and then it just collapses down to something small. And it's called that because of the old telescopes that you might have seen like in pirate movies, where it's a horrible picture of a telescope. But basically, you extend it out, you put your eye here, and you look through here, and then you see the ships that you're about to raid. Okay. But when it's time to put it away, this piece slides into here, this piece slides into here, this piece slides into here, so it collapses down to something small. Okay. So what's going to happen is we get just the limit as n goes to infinity of just the pieces that don't cancel. So f of x sub n minus f of x sub 0, or x naught. But I actually know x sub n, that was my rightmost endpoint, and x sub 0, that was my leftmost endpoint. So I'm getting the limit as n goes to infinity of f of b minus f of a. There are no n's in that. That's constant with respect to n. I'm going to get f of b minus f of a, which is exactly what the fundamental theorem says. So back when we learned the mean value theorem, it seemed kind of weird that we had this theorem that said there's a point out there that has this property, but the theorem didn't tell me how to find exactly what that point was. And I mentioned that there are times when it's just useful to know that there's a point with a certain property, even if you don't know exactly what it is. This is one of those times. Knowing that I could write f prime at xi star as the slope of a secant line on f, that was what allowed me to switch from talking about f prime in my sum to talking about f, which is where I knew I wanted to go. Again, you are not responsible for being able to prove the entire fundamental theorem of calculus on your own. That would be asking a bit much. But I do want you to take a look at this and read through it a couple of times. So I could ask you some questions about some individual parts of it. So you should be prepared for that.